Okay, welcome everyone. So today we are going to solve the problem called maximal square. Okay, so in first look, this problem seems a bit difficult, but it's a medium level problem, and once I'll explain you how things are working over here, the building blocks of the problem, then it will be easy for you to code the solution as well. Okay, so we will have a m cross n matrix. Okay, and matrix will have zeros and ones, and from these zeros and ones we have to identify the maximum square which had all ones. So for example, here this particular square, this is going to be a square of length, rather square of area 4, because there are 4 ones in it. And similarly, this square which has all ones in it, and its area is also 4. So answer in this particular block of input should be 4, because maximum square that you can form from all ones, you know, is 4. So if this part is clear to you, let's go to the building blocks of the problem. Okay, so the first case, first building block, let's assume that you have just single cell. Okay, single cell that has 1 in it, like this one. Okay, a single cell. So in this case, the maximum answer that you can find is actually 1. Okay, does that make sense? Because this is just a single square which has 1 in it. Okay, and since this is single cell, we can return 1. Okay, now what will happen if a position is invalid? Now what the invalid position means, so we have seen this in the earlier examples as well. So if this is my problem statement, so anything which is out of bounds of this problem statement is actually an invalid cell. Okay, so for example, this part, then this part, then this part, then this part. Okay, these all are invalid cells. So in that case, they will not add into the solution, right? They will not benefit the solution, benefit the final answer, because those are from the invalid positions. Hence we have to return 0. Okay, now assume that you have a square, a single square which has 0 in it. Okay, the problem states that we have to find a square, the maximal square, which has 1 in it and not the 0. So in case if you see there is 0 anywhere, you will do nothing, right? You will keep that value as is. Now if these 3 building blocks are clear to you, we can now talk about the bigger squares. Okay, so as you can see, this particular square, okay, we have 1 over here, 1 over here, 1 over here, 1 over here. Now this complete square becomes, I mean, area of all of these ones will become 4. How? Because it has all the elements, all the components of this square are actually ones. Okay, does that make sense? Okay, so how we will identify if any of the predecessor, you know, if we have 1 over here, 1 over here, 1 over here, then are these ones going to affect what comes over here? Okay, so if this value is also a 1, that means we actually have a combination of 1, 1, 1 and 1. Okay, and now we can say that we have formed a bigger square, correct? Because since this value is 1, the value above is also 1, the value diagonal to it is also 1, the value to the left is also 1. Hence this candidate, I mean this particular cell, will form a bigger square. Okay, is it making sense? So that is what I have tried to write over here. So if you see this, you see this, a 1 is over here. Okay, I'll erase this 2 as of now. So imagine this was actually 1. Okay, the element above it is 1, the element diagonal to it is 1, the element to the left is 1. This means this 1 is a part of a bigger square. Okay, and hence I'm going to change this value to 2, because if I include this part, this particular one over here, I will form a square which has diagonal as 2. Okay, now if we want to generalize this, okay, based on our observations so far, if we want to generalize this, the value of any particular cell, for example this, depends on the top cell, the diagonal cell, and the left cell. Okay, and if suppose one of these values was 0, okay, so in that case what will happen? Will this value be 2? No. Why? Because for to form a bigger square, it is extremely important that all of the values that are above it, that are diagonal to it, that are to the left, okay, if those values are 1 1 1, then only we can form a square of length 2 over here. Okay, similarly, just assume that there is one more case, okay, where you don't know what is over here, what is over here, the above cells are not known to you. You just know that here I have 3, here I have 3, here I have 3. That means, okay, that means what will go over here? Okay, so for this particular cell, the above value is 3, the value to the diagonal is 3, and value to the left is also 3. That means these elements are already part of a bigger square, and now we are just talking about what will happen if we add this particular one to the already formed square. Will it form a bigger square? Okay, so from this 3 3 3 we can say if all of these are part of a bigger square, then adding this one is also going to be even bigger square. Hence I will put value of 4 over here, right? So if this part is clear to you, now we can come back to this particular part. So here we have established that if the above value, the diagonal value, and the left value are same, then we have to increment it by 1. But what if they are not same? Okay, that's the case which we are trying to discuss over here. Here this 0 is not 1, so this is not part of any square. This one is actually part of a square of length 1, and similarly this one is part of a square with length 1. So in that case, even if we have 1 over here, it will not add any benefit. Okay, it will not be a bigger square because of this particular cell. Okay, as this particular cell is not 1, adding this 1 is not going to increase the area of square. Okay, hence we can simply say that based on the above observation, we can say the minimum, okay, the minimum of these 3 values. Which 3 values? The above one, okay, the diagonal one, and the left one. Minimum of these 3 values plus 1 is going to be value of any particular cell. Okay, so here it was 3 3 3, hence we made it 4, because minimum of 3 3 3 is 3, and 3 plus 1 is 4, hence we put it as 4. But here in this example it is 0, 1 and 1. Okay, and because in 0, 1, 1 the minimum is 0 and 0 plus 1 is actually becoming 1. Okay, hence we can say that the new solution should be minimum of these values plus 1. Okay, now if we move ahead and try to generalize this solution, we can say that this value of any particular cell can be minimum of up, left, diagonal plus 1. Okay, so if you apply set the same logic over on this particular block, all the invalid locations will return 0. Okay, then let's start from this cell. Okay, for this cell the value depends on this, this and this. Okay, so since this is 0, this is 0, this is 0, 0 plus 1 becomes 1, and hence the value is 1 over here. Similarly for this cell, it all depends on this plus this diagonal, and this is 0, 0, 1. The the minimum out of this is 0, and 0 plus 1 is 1, hence I'll keep it as is. Okay, similarly you can compute for this and this, the values will be 1 and 1 itself. Okay, now what about this second row? Here you will find 1 over here, this is invalid position, hence we will return 0, and this is invalid position, hence we will return 0. Now 0, 0, 0, 0 and 1 are the combinations out of which 0 is minimum, hence this will also be 1. But the game changes over here, right? In this case, the above value is 1, the diagonal value is 1, the left value is 1. So minimum of 1, 1, 1 is actually 1, and hence I can change this value to 2. Okay, now moving on. Similarly for this particular square, the above is 1, the diagonal is 1, the left is 1, hence this can also become 2, right? And similar logic is applied over here. So in this case, above is 1, diagonal is 1 and left is 2. Okay, and the minimum is 1, so 1 plus 1 is 2, and hence we can say that this square is also part of a bigger square, and hence we'll put it as 2. Now similarly going ahead, for this particular part we see that here we have 2, here we have 1, here we have 0. Minimum is 0, 0 plus 1 is 1, hence we'll keep it as 1. In this case we have 2, 2 and 1, so minimum 2, 2 and 1, the minimum is 1, hence 1 plus 1 is 2, hence we can say this square, if we add it, it will form a bigger square of diagonal 2. Okay, similarly over here, this is 2, this is 2, this is 2. Now if you observe over here, the minimum is 2, and hence we will put 3 over here, right? And if I have to highlight the square that has 3 as a diagonal length, then it becomes this square. Okay, now I think you guys must have understand that how we are going to use the earlier computations to find the new results. Okay, so if this part is clear to you, you can refer to this code. Okay, so in here what I have done is I am creating a 2D array over here. Okay, I'm going through each row and each column combination. Each time I am getting the upper value, the diagonal value, and the left value. This in the same way that we have observed so far. I have written a method called get value. Okay, so what the get value does is, if there is any invalid combination, okay, so here in this case, any invalid combination will return you 0. Okay, and all of the valid combinations, depending on which option you are sending, so you can have option as D or U or L, indicating the upper cell value, I mean get me the upper cell value, or get me the down cell value, or sorry, diagonal cell value, or get me the left cell value. And depending on the option which you send from here, we will return the respective values. So this is just one additional method which I have written, so that my overall logic which comes over here is a bit clean now. Okay, so based on these three values, I'm going to find the minimum. Okay, I'm going to find the minimum, and I will put the value as whatever minimum I have found so far, plus I will add 1 to it. Okay, here is that logic where I am adding 1 to it, and on the way I'm keeping track of maximum value that I have found so far. Okay, so max I have initialized it with 0 over here, so I'll update the max based on the maximum value that I already know, plus the maximum value that I have computed so far. Okay, and at the end I will return answer as maximum into maximum, because the whole effort, in this whole effort, we are actually finding the diagonal, right, length of the diagonal. Okay, but the final answer is not the length, is asked to us that what is the area of this particular square, not the length of the diagonal. So hence, if this is of 3, so the length of diagonal is, let's say, 3, then the area becomes 3 into 3, that is 9, and hence I am returning max into max over here. Okay, so if this part is clear to you, I would request you guys to follow the code and do the dry run yourself, go through the base cases, and then grow on top of it, so that you will get a better understanding of the code.